Welcome to G Fun Facts Online. Today, we're venturing to the bottom of the world, to a continent of extremes, breathtaking desolation, and untold secrets, Antarctica. Beneath a formidable shield of ice, averaging over 2 kilometers thick, lies a land that holds the key to understanding profound shifts in Earth's climate, the assembly and breakup of supercontinents, and the intricate dance between solid Earth and unimaginably vast, moving ice masses. Probing its ancient bedrock and the ever-shifting ice above is like assembling a colossal, three-dimensional puzzle, with each new discovery revealing another piece of a story stretching back at least 300 million years, and often far beyond. So let's peel back the ice and explore the geological heart of Antarctica. Antarctica wasn't always the isolated, ice-covered landmass we see today. Let's rewind the clock about 300 million years. Back then, during the late Paleozoic era, Antarctica was a central piece of Gondwana, a massive supercontinent that also included what we now know as South America, Africa, India, and Australia. Gondwana itself was part of the even larger supercontinent, Pangaea. Imagine Earth's landmasses all snuggled together. The rocks of Antarctica still bear the scars and imprints of these ancient connections and the fiery rifting events that eventually tore these supercontinents apart, sending Antarctica on its lonely journey towards the South Pole. Geologically, Antarctica is a continent of two halves, split by the iconic Transantarctic Mountains. You have East Antarctica, the ancient, stable craton, with rocks dating back over 3 billion years in some places. Think of it as the old, wise elder of the continent. Then there's West Antarctica, a geological youngster, a mosaic of smaller crustal blocks welded together over the last 500 million years. This region is far more dynamic, home to the West Antarctic Rift System, a massive zone of crustal stretching comparable to the East African Rift. This rifting has thinned the crust, sparked volcanic activity, and created deep subglacial basins, some lying more than 2.5 kilometers below sea level. This geology, especially its low-lying bedrock, is super important for the stability of the West Antarctic ice sheet, but more on that later. Speaking of mountains, the Transantarctic Mountains are one of the longest mountain ranges on Earth, stretching over 3,500 kilometers and acting as a spectacular barrier between East and West. Some peaks tower above 4,500 meters, offering rare glimpses of the continent's bedrock and a history of uplift and erosion. But perhaps even more astonishing are the Gamburtsev subglacial mountains, entirely hidden beneath kilometers of ice in East Antarctica. Discovered by a Soviet expedition in 1958, these mountains are as big as the European Alps. Their existence in the stable interior of East Antarctica was a huge puzzle. It's thought they first rose over 500 million years ago, were eroded down, then rejuvenated before the ice sheets entombed them, preserving their alpine shapes. The Gamburtsevs are even believed to have been a key starting point for the massive East Antarctic ice sheet. Now, here's a mind-bender. Antarctica wasn't always a frozen wasteland. Around 300 million years ago, despite Gondwana's polar position, there's evidence of widespread glaciation. But, and this is a big but, the continent also experienced much warmer climates. Fossil evidence of forests, including the seed fern Glossopteris, found in the Transantarctic Mountains, proves that trees once grew there, even when Antarctica was near the pole. The journey from these temperate, sometimes even tropical conditions, to its current deep freeze state is a fascinating tale of continental drift, changing ocean currents, and a big drop in atmospheric carbon dioxide levels over millions of years. The big chill that led to Antarctica's current icy state was a long process. Around 34 to 37 million years ago, mountain glaciers started to appear. A major turning point was the Eocene-Oligocene boundary, about 34 million years ago. This marked the first widespread glaciation and the initial formation of a continental-scale ice sheet, mainly in East Antarctica, linked to falling CO2 levels. Critically, as Antarctica separated from Australia and South America, the Drake Passage opened up. This allowed the Antarctic circumpolar current to form a powerful ocean current that thermally isolated Antarctica, basically putting it in a planetary freezer and intensifying its cooling. Through the Miocene, roughly 23 to 5.3 million years ago, the East Antarctic ice sheet largely stabilized, while the West Antarctic ice sheet began its more dynamic existence, growing and collapsing at times. By about 14 million years ago, a more complex ice sheet system was in place. And over the last 5.3 million years, the ice sheets, particularly in West Antarctica and the Antarctic Peninsula, have continued to fluctuate dramatically. So how do scientists know all this, with all that ice in the way? It takes some incredibly clever techniques. Ice-penetrating radar acts like an X-ray for the continent, allowing scientists to map the bedrock topography, find hidden lakes, and trace layers within the ice. Seismic surveys use sound waves to image rock layers beneath the ice. Satellites precisely measure the ice surface, revealing the subtle dips and rises that betray underlying mountains and basins. Gravity and magnetic surveys help infer the types of rock hidden below, but it's not all remote. Scientists also drill deep. Projects like ANDRIL and the International Ocean Discovery Program have retrieved sediment cores from the Antarctic margin, providing invaluable records of past ice sheet behavior and climate. And one of the most exciting frontiers is drilling into subglacial lakes. Teams have successfully drilled into Lake Whillans and Mercer Subglacial Lake, boring through nearly 1.2 kilometers of ice in the case of Mercer. They found surprisingly rich microbial ecosystems and sediments that offer clues to past ice sheet stability. Back in the lab, tiny zircon crystals from rocks act as mineral time capsules, dated to reconstruct ancient mountain-building events. Isotope geochemistry analyzes chemical signatures to reveal past temperatures and carbon cycles, while microfossils in sediment cores paint pictures of past environments. The relationship between Antarctica's bedrock and its ice sheets is a complex, dynamic dance. The shape of the land beneath the ice dictates where ice flows fastest, channeling it into ice streams. In West Antarctica, where much of the bedrock is below sea level, the ice sheet is particularly vulnerable to warm ocean water sneaking in and melting it from below. The discovery of over 675 subglacial lakes, some vast like Lake Vostok, has been a game-changer. These lakes aren't static. They fill and drain, lubricating the base of the ice sheet and influencing its flow. And yes, there's geothermal heat from Earth's interior, which can melt the base of the ice sheet, especially in volcanic West Antarctica. As the ice melts and its immense weight is removed, the bedrock slowly rebounds. This isostatic adjustment is happening now and could actually play a role in future sea level rise by altering ice sheet stability. Why is all this ancient geology and ice dynamics so critical today? Because Antarctica is ground zero for understanding our planet's response to climate change. Take the Thwaites Glacier in West Antarctica, often called the Doomsday Glacier, and its neighbor, Pine Island Glacier. These are among the most rapidly changing ice masses on Earth. They flow over bedrock that deepens inland and sits below sea level, making them highly susceptible to melting from warm ocean water getting underneath. The potential collapse of Thwaites alone could raise global sea levels by over half a meter, and it acts as a plug for an even larger area of the West Antarctic ice sheet. By studying how Antarctic ice sheets responded to past warm periods, scientists can improve models that project future ice sheet behavior and sea level rise. Knowing the exact shape of the bedrock under these critical glaciers is vital for reducing uncertainty in these projections. Despite incredible progress, many pieces of the Antarctic puzzle are still missing. What are the precise conditions beneath vast unexplored areas? How interconnected are the subglacial water systems? How quickly can the bedrock respond to ice unloading? These are urgent questions. Chinese scientists recently discovered 46 new subglacial lakes, highlighting just how much there is still to learn. Antarctica's bedrock geology, forged over hundreds of millions of years, provides the fundamental template for its immense ice sheets. The dynamic interplay between this hidden landscape and the ice above has shaped the continent's past and will critically influence its future, and consequently, the future of global sea levels. As we continue to probe deeper, each discovery helps complete the Antarctic puzzle, revealing not just the secrets of a frozen continent, but vital clues about the workings of our entire planet in an era of unprecedented change. Thanks for joining us on G Fun Facts Online. Until next time, keep exploring.